Welcome to the next short video clip. In this video clip I will demonstrate something that is in German called Vibrationslautsprecher. And the reason for this clip is that I think it's a very good illustration of the next presentation with the theme sound radiation. So this is the Vibrationslautsprecher placed on my desktop here, and through the cable you see here you can feed it with the electric signal. So if I start the electric signal now by now it's running. Maybe you hear something, but maybe not. And if I place it now on the table here, you will hear the difference. I put it up again and place it here again. So what is happening? How can you explain this dramatic difference in sound? So, as you know, if we have a vibrating surface that enforces motion in the surrounding air, then we will have a sound wave. This, for example, this guitar box, when we pluck a string, it will start vibrations in the walls of the guitar body. And of course, this vibration will contribute to the sound field that is radiated by the guitar. So how can we calculate or model the contribution to the sound field from the guitar body vibrations? So that is something that we will discuss more in this presentation. So let's start with a simple example. Suppose we have a very large, almost infinite plane surface that vibrates with all points in phase and with the same amplitude. So we have here then the rigid wall that vibrates with a single frequency. So then we will of course get a plane sound wave that radiates from the plane surface, vibrating surface. And the sound intensity in the field outside this wall can be, the time average of this sound intensity can be calculated with complex sound pressure times the particle velocity in the normal direction of the vibrating surface. And then we take the real part of this and multiply with half. That will give us the time average sound intensity. Now, if we want to transform this to the wall vibration properties, then we have to use the boundary conditions, and we can find this expression here. So first of all, we have to take the specific acoustic impedance of the medium outside the wall, rho C, and then we multiply with the normal component of the wall, the surface vibration velocity. And we should, of course, take the root mean square of it. So this will give us the time average of the radiated sound intensity. So if we now consider the sound power emitted to the surrounding media, then if we take this subsurface area, ds, then we get the time average radiated sound power by multiplying the time average sound intensity with the size of the radiating surface. So this will now give us the contribution from the surface part ds to the radiated sound power, the time average of the radiated sound power. So if we now want to generalize this to a general shape form of the vibrating surface, then we can simply sum the contributions to the radiated time average sound power from all small surfaces here, ds surfaces, as a surface integral like this. And so this is the radiated sound intensity then from this small area ds here, and then if we sum this over the whole vibrating body, we get the total time averaged radiated sound power. Now we can simplify this by substituting the complex sound power by the product of the radiation impedance and the vibration velocities normal component in the point we consider. And then after some complex algebra, we find this expression for the time average of the radiated sound power. This radiation impedance is, of course, a function, a complex function of the properties of the medium outside, of course, and also the surface shape and the vibration field characteristics. If it's torsion waves, bending waves, or other types of waves, this has a great influence of the radiation impedance. So in practice, this is a very difficult problem, and we have to use finite element models or similar models, numerical methods, to solve this problem, to calculate the radiated sound power. But in some cases, some simple cases, we can do it manually by hand. And now, if we go now to the simplified method I mentioned in the beginning, then what we first do to get a simplified version of this integral formula is to replace the radiation impedance with the medium's specific acoustic impedance, this rho C. So the surrounding medium's specific acoustic impedance we use as radiation impedance. This is, of course, a great approximation. Then we replace the mean square normal component of the vibration velocity in the specific point we consider by the spatial average over the full vibrating surface. This parenthesis here denotes the spatial average. And what we get then is actually the sound power radiated by a very, very large flat surface with all points vibrating in phase and the same amplitude. It's exactly the same form as the radiation from the large piston as we saw previously. So this is now the simplified version of the time average radiated sound power from this general shaped vibrating surface. Now, this is maybe too crude. So in order to get a better approximation, we try to sort of incorporate the shape, the properties of the radiation impedance, the shape of the vibrating body and surface and so on, by introducing something that is called the acoustic radiation efficiency, denoted with small s. So what we do now is to replace this surface integral by the specific acoustic impedance of the surrounding medium, by the spatial average of the mean square normal component of vibration velocity, and this radiation efficiency, S. So this S here depends on the shape of the body, the surrounding media, and the characteristics of the vibration field. As I said before, in some cases it's possible to calculate without numerical techniques like finite element methods this radiation efficiency. So the first example of this is a very, very, very large, undeformed, flat, and in phase with same amplitude vibrating surface. This is the very, very large piston, as we saw before. And as we saw before, the time average of the radiated acoustic power is this. So in this case, if we compare the expressions here and here, we see that the radiation efficiency is actually equal to 1 in this case. So that is the most simple case. Next example, that is a sphere. Suppose we have a sphere with a pulsating radius A. That is, we have that will create then a spheric, angular symmetric, spherical symmetric wave field around the sphere. And as we've seen in another presentation, the radiated sound power looks like this. Here we have the sphere surface, and then the root mean squares of the sound pressure and particle velocity evaluated at the surface of the sphere. So in the previous presentation on spherical waves, we found that that we can express the root mean square of the sound pressure at the surface in terms of the vibration velocity's normal component, like this. K here is the wave number, and here we have the specific acoustic impedance of the surrounding medium. And of course, at the sphere surface, the particle velocity should be equal to the normal component of the sphere vibration. So if we introduce this, we find this expression for the radiated sound power. And by comparing now with this expression, defining expression for the radiation efficiency, we can see that the radiation efficiency for a pulsating sphere looks like this. So it's a pure function of the wave number times the sphere radius. And if we plot it versus the wave number times the sphere radius, this is actually proportional to the frequency. So the horizontal axis here can be seen as a frequency axis. And as you can see here, for low frequencies, low wave numbers times radius, the radiation efficiency is very, very low. So a pulsating sphere at low frequencies is an inefficient sound radiator. But as the frequency of the vibration, the pulsations increase, the efficiency increase more and more. And it's, as you can see here, it tends to 1. So for high frequencies, the radiation efficiency of a pulsating sphere is almost the same as a very, very large piston. Next example. Let's say we have a very large, flat, lossless plate that performs bending vibrations. Then we can show by simple pen and paper methods that the time average of the radiated power looks like this. So here you can see again the specific acoustic impedance of the surrounding medium and the spatial average of the normal component of the mean square vibration velocity. And this is then the surface area of the bending vibrating plate. And then we have the real part of 1 over the square root of 1 minus a ratio Fc over the frequency. And this Fc is what is known as the coincidence frequency. And the coincidence frequency is defined as the frequency where the phase velocity of the bending wave is equal to the speed of sound in the surrounding air or in the surrounding medium. So with the Bernoulli-Euler model for bending waves in the plate, we get this expression for the coincidence frequency. As you can see here, well, C here is the speed of sound in the surrounding medium. And here we have the plate's material parameters and the thickness of the plate. And the radiation efficiency then in this case becomes the real part of 1 over this square root. So if we plot the radiation efficiency versus the ratio of the frequency and the coincidence frequency for this very, very large bending, vibrating, lossless, flat plate, we get a curve like this. So when the frequency, bending vibration frequency, is lower than the coincidence frequency, then the radiation efficiency is 0. Then when it's equal to the coincidence frequency, then it turns out that we get infinite radiation efficiency. And then as we increase the frequency to higher values, it will gradually decrease to radiation efficiency equal to 1. So, a very large, flat, lossless plate performing bending vibration. So what can we say about this? How can we interpret this physically, this strange behavior? Well, first of all, for the frequencies below coincidence frequencies, then, as you know from the definition of coincidence frequency, the bending waves will be subsonic. And this means that the air is oscillating between regions vibrating in opposite phase. So when the air is pushed up here in this region, for instance, then it has time to move to the opposite phase regions in the neighborhood of this positive phase region. So since the bending waves move so slower than the speed of sound, then the air have time to move to the negative, to the opposite phase regions, and there will be no radiation of sound to the far field in the air surrounding the plate. So no sound radiation in this case. Above coincidence, then we know that the bending waves are supersonic. They move very, very fast compared to faster than the sound waves in the surrounding medium. And that means that the air does not have time to oscillate, to fully cancel out the sound radiation by oscillating between negative and positive phase regions like this. So this means that we will get sound radiation in this case above coincidence frequency. So the conclusion then we can draw from this example is that if we want the bending vibration field excited by our vibrationslautsprecher, as you can see in the starting video clip, if we want it to radiate the proper sound, I mean the music as it should be heard, then we must choose a desktop or whatever radiating surface we choose, with a radiation efficiency close to 1 for all frequencies that we are interested in. So that is an important conclusion from this discussion we've had.